also be applied in different contexts. But inflation is a phase of accelerated expansion that took place at very early time in the universe. So it's an epoch during which the scale factor is not only growing, but it's accelerating. And during this phase, there is one parameter, which we call the Hubble parameter, A dot over A, which characterizes the expansion, which is the rate of the expansion. So it characterizes the curvature of space-time. So 1 over h has the dimension of a time scale or a dimension of a length scale if you set the speed of light to be unity. And therefore, if you put a quantum field on top of this expanding background, if you Fourier expand this field, then the dynamics of each Fourier mode pretty much depends on whether the wavelength associated to that mode is smaller than the Hubble radius or larger than the Hubble radius. So if it's smaller, it means that you locally see, I mean, this mode locally sees a flat space-time. So exactly in the same way that if you perform an experiment in your office, you don't have to take into account the fact that the Earth is curved because the radius of the Earth is much larger than the size of your office, if you have a reasonable sized office like me. But on the other hand, if the wavelength is much larger, then you need to take curvature into account. And what happens during inflation is precisely that you have a transition between this regime on the left-hand side and this regime on the right-hand side. So what happens is that during inflation, this Hubble radius is almost a constant. Wavelengths of the different Fourier modes, they grow as an effect of the expansion. So initially they lie inside the Hubble radius. You can set out initial conditions in the vacuum state of flat space-time. And then at some point they cross out the Hubble radius, which means they feel the effect of the curvature. And when you have a quantum field on top of a curved background, you typically have quantum particle production. So in this super Hubble regime here, you have explosive production of particles. And those quantum particles, they end up providing the seeds for the fluctuations that we see either in the cosmic microwave background. Here is a map of the temperature anisotropies taken by the Planck satellite, or indeed in the large-scale structure of the universe at later time. So by observing those, we can infer some information about the physical processes that occur during inflation. Now, the way that this standard calculation is usually done is in the context of what is called cosmological perturbation theory. And in this talk, I will try to argue that in some cases we need to go beyond that. But let me first recall how cosmological perturbation theory works. So the idea is that if you want to explain, for instance, temperature fluctuations on the cosmic microwave background, because they have a small amplitude, you can use a perturbative approach. So you take the full metric and say the field. So here I assume that inflation is driven by a single scale field for simplicity. And you expand those objects onto a classical function of time only, so a homogeneous component, which is a solution of the classical problem, so no quantum effects here. And then you add a small fluctuation and you quantize only those small fluctuations. So it's sort of a semi-classical or semi-quantum approach. You don't quantize the full metric, of course, because we don't know how to do that. You only quantize fluctuations. And when you do that, you end up with a quantum field theory in a curved space-time, and we have techniques to solve such quantum field theories. However, this relies on a rather strong assumption, which is that the universe is quasi-homogeneous and isotropic at all scales, because you're expanding those objects at all scales. However, we only know from observations that it's almost homogeneous and isotropic at CMB scales. So this assumption could be either broken at large scales or small scales. If it's broken at large scales, it means there is a structure to the space-time beyond the observable universe, which is a possibility. Of course, it's difficult to probe because by definition, it's beyond observable scales. If it's broken at smaller scales, then it could give rise to the formation of extreme objects, such as primordial black holes, and this is what I'm interested in here. Okay, so what I would like to be able to do is describe a regime where those fluctuations become large, sufficiently large to produce primordial black holes, and such that I can't just use this cosmological perturbation theory. So the outline of the rest of my talk is the following. I will explain how I can go beyond perturbation theory using an approach which is called the stochastic delta rand formalism. And then I will explain how within this formalism one can compute the statistics of cosmological fluctuations. And depending on how much time I have left as an application, I will show what consequences this gives for abundances and mass distributions of primordial black holes, as well as maybe other cosmological observables. So the stochastic delta N formalism relies on two main ingredients, which I now briefly discuss. The first one is the so-called separate universe approach, and the second one, which is related, is what is called delta N formalism. So the separate universe approach works as follows. If you write the metric in this way, so you just redefine time with conformal time eta. In an accelerating background in a quasi-de Sitter universe, the scale factor depends on time in this way. So eta goes from -infinity to 0. So this is the asymptotic future of the Sitter space-time. This is time, this is space. And the advantage of using conformal time is that light propagates in straight lines in this diagram. So if you take a certain time during the evolution, and you look at those 2 points at the intersection between the orange lines and the black dotted lines, they are such that if they emit a photon towards each other, those photons, they will meet only in the asymptotic future. So it means that if you take 2 points which are separated by a distance larger than this co-moving Hubble radius, then they don't have any future contact, causal contact. Of course, if you trace back the light rays backwards in time, you find that at some point they intersect. So they do have a past causal contact, but not a future causal contact. But the idea is that because of that, if you consider cosmology at two locations, x1 and x2, which are distant by a distance which is larger than the Hubble radius, then what happens here cannot influence what happens there, right? So if a large quantum fluctuation, for instance, develops at x1, it has no consequence on the local geometry in the future of x2 because of this space-time structure. And because of that, one can design what is called a separate universe approach, which essentially tells you that on large scales, so on large distances, larger than the Hubble radius, we can describe the universe by a collection of independent patches, locally homogeneous and isotropic patches, and all of them are independent. Okay, so it's another way to implement what is sometimes called the gradient expansion approach, the fact that you can neglect gradients on super Hubble scales. And I know that tomorrow there will be a presentation by Naruko-san about the gradient expansion approach. So I guess you will learn more about this tomorrow. So the idea of the stochastic inflation formalism is to separate scales between what is inside the Hubble radius and what is outside the Hubble radius. What is inside the Hubble radius is physics which happens on locally homogeneous and isotropic universes. So we can use cosmological perturbation theory to describe sub-Hubble scales. While for what happens in the super Hubble sector, we're going to use something better, which is stochastic inflation, right? So the idea is that we want to coarse grain our fields to only keep fluctuations above the Hubble radius and design an effective theory for those objects. So we consider a certain scalar field phi. Here it's the inflaton, but it could be anything. And at a certain time n is just the number of e-folds, it's just a way to label time, and it's log of a. And what we do is we Fourier expand this field, and we only keep those Fourier modes k, which are smaller than the Hubble radius, with a certain parameter sigma, which is called the coarse graining parameter, and which will not play a role, which will just drop out from calculations in a minute. So the idea is to design an effective theory for that guy, and this can be done in a very refined way using standard effective field theory techniques, so integrating out in the action and so on. But if you just want to get a heuristic and schematic sort of explanation of what's going on, you can see that if you wanted to derive, say, an equation of motion for that guy, so if you want to do d phi over d time, then there are two terms on the right-hand side. The first one comes from the fact that the mode functions depend on time. But because of the separate universe approximation, since those are Fourier modes with a small k, so they correspond to very large scales, they behave as, remember, an independent collection of homogeneous and isotropic patches, which means that their equation of motion is essentially coincides with the one of the background. So on the right-hand side, you have this first term, which you would also obtain for just at the classical background level. But then you have a second term, which comes from the fact that the lower bound of this integral depends on time explicitly through this scale factor a of n, and also the Hubble parameter can also slightly depend on time, which gives you an additional term here. And this term here corresponds to the fact that physically, if you define your system as being all the stuff above this blue line, at every instant of time, you have wavelengths crossing out the Hubble radius, so they join this coarse-grained sector. So, and this gives this contribution, this psi here. So quantum fluctuations source the dynamics of the background just because Fourier modes cross out the Hubble scale at every instant of time. So this is the essence of the stochastic formalism, which was proposed by Alexei Starobinsky in 1986, with some already some early works in 1982 as well. And the idea is to see this equation not as an equation for a quantum field, but as an equation for a stochastic field, right? So phi is promoted to a random variable, and psi here becomes a Gaussian noise. Gaussian because, okay, in cosmological perturbation theory at leading order, fluctuations have Gaussian statistics, and we just replace this psi by a Gaussian noise. Now, there is an argument which is often mentioned and which is supposed to show that stochastic effects are always small. And the argument is as follows. If you consider a typical timescale of 1 e-fold, and you look at the ratio between the quantum jump, so the one generated by this psi here, divided by the drift induced by the background dynamics, then you obtain something which scales in exactly the same way as the amplitude of the curvature perturbation that you obtain from a classical calculation. And because curvature perturbation is small, then you know this ratio is small, and therefore stochastic effects do not play a big role. However, there are two things which might make the simple argument not universal. The first one is that it is derived using a classical calculation. So if you're far from the classical regime, you cannot trust this estimate at all. And indeed, I will show cases where stochastic effects strongly dominate. So this ratio is basically large, but still the curvature perturbation is small. And the reason is that this relationship, again, assumes that stochastic effects are small from the beginning. And the second reason why you might want still to include stochastic effect is that this is true for the typical curvature perturbation, but it's not true for what happens on the tail, right? So for those rare, large curvature fluctuations. And because those large fluctuations are precisely what give rise to primordial black holes, which is what we're interested in, so we are interested in the tail of the distributions of density fluctuations, then it also means that we might have to want to go beyond just a classical level. And I will show explicit examples in a second. So now the question is, given this stochastic picture where the fields evolve with stochastic equations, which we call Langevin equation, well, the question is, how can we do to extract information about density fluctuations, their distribution function, the power spectrum, and cosmological observables in general? And this can be done using what is called the delta N formalism, which is the last ingredient that I want to introduce, and which works as follows. So the delta N formalism is a result which states that, on separate Hubble scales, if you look at the initial hypersurface, which is spatially flat, and a final hypersurface, which has a uniform energy density, now you can count how many, for a certain co-moving observer, you can count how many e-folds you realize between those two surfaces. This is called n of t and x, because it depends on this local observer. And of course, a slightly shifted local observer will measure a slightly different number of e-folds. And if you take the difference between those number of e-folds, which we call delta N, this essentially coincides with the curvature fluctuation, okay, at least on large scales. So why is that useful? It's because if you know something about the statistics of n, about the statistics of the amount of expansion, then you directly infer something about the statistics of your curvature fluctuation. Okay, so the idea is the following. We have a certain stochastic process. So schematically, it means that starting from a certain initial condition for the field value, the evolution of the field value will have a noisy stochastic trajectory. And at some point, it will cross the end of inflation surface, and we can look at how many e-folds it has realized. So N1 in the red trajectory. Now you can do this process another time, and then you will simulate another realization of your stochastic process. This other realization will produce a different number of e-folds, N2. And then you can go on like this again and again and again. And then what you do is you produce a set of values for N, which gives support to a certain distribution function for N. And this distribution function for N, which I call calligraphic N here, is essentially the distribution function of your curvature fluctuation. Okay, so the idea is that we want to compute statistics of perturbations in this way. So this is what is called the stochastic delta run formalism. Now, at the technical level, what you need to do is to compute what is called the statistics of first passage times. So if I go back to my previous slide, I want to compute the statistics associated with this first passage time, so the time of the first crossing of the end of inflation surface. And this can be done in several ways. You can do it numerically, the way that I just said. So you simulate a large number of realizations, and you look at how many e-folds you've produced, and you record the number, and you do it again and again and again. But this is numerically quite expensive because you have to produce many realizations. Also, if you want to sample the tail correctly, it means you need to have a huge statistics, because the tail is, of course, a rare thing. You can also approach the problem analytically, and I just quickly explain how. So this is the stochastic equation, the Langevin equation you get for a single scale field in expanding in a quasi-flat potential, rolling on a quasi-flat potential. Of course, this technique can be generalized to other models, multiple field models, non-serval models, and so on. But the point is that it always boils down to a Langevin equation. And from this Langevin equation, you can infer what is called the Fokker-Planck equation, which is equivalent to the Langevin equation, and which tells you how the evolution of the distribution function of the field value evolves. So you start your process at a certain initial value for phi, and then you ask the question after n equals, where is phi? And the answer is, well, it's given by a certain distribution function, which is this p of phi and n. And this p of phi and n obeys this equation. dp over dn equals a certain differential operator, which we call the Fokker-Planck operator, acting on the distribution itself. Now, something we have been able to show is that, in fact, a very similar equation exists for this calligraphic p, which, however, this calligraphic p is completely different from this straight p. So calligraphic p is the distribution of first passage times. So now the question I want to ask is, starting from a certain initial field value, which I call phi, how many e-folds do I realize until inflation ends? And I call this number of e-folds calligraphic n. So it's a distribution of n given phi. And then you can show that it obeys almost the same equation as this Fokker-Planck equation. So d calligraphic p over d calligraphic n is some operator acting on p, and this operator is the adjoint of the Fokker-Planck operator, okay, which means it can be simply derived from the Fokker-Planck operator. So this is just a partial differential equation. In some cases, it even have analytical solutions, or you can try to solve it numerically. And this gives another way to reproduce the statistics of first passage times. So the computational program of the stochastic delta run formalism is the following one, to summarize a bit. So the first step is you solve the first passage time problem. So either by solving this equation or by simulating many realizations of your stochastic process. Then once you have reconstructed the distribution function of n, it means you have reconstructed the distribution function of the curvature perturbation if you coarse grain it at the Hubble scale at the end of inflation. Of course, this is not necessarily the object that you want to have. Maybe you want something else. Maybe you want the power spectrum. Maybe you want the like abundance of black holes and so on. So maybe you want the distribution function of the density fluctuation instead of the curvature fluctuation, and maybe you want it coarse grained at a scale which is not the Hubble radius at the end of inflation, but which rather corresponds to, I don't know, the mass of a black hole you want to study and so on. But then there is a third step, which consists in extracting, well, those relevant quantities that you might be interested in from the knowledge of zeta coarse-grained at Hn. So this is the third step, and of course it can take, I mean, you might want to follow different routes depending on what you want to do. So what I will do is, is try to illustrate a bit this procedure and give you some results which are as much model independent as possible. So of course the details depend on the model, but then there are a few facts which happen to be completely model independent. And the first fact is that the tail of the first passage time is always exponential. Okay, so this is something that we managed to show in those two papers, that in fact on the tail, you can always expand the distribution function of the first passage time in this way. So you have a sum of exponential with some eigenvalues lambda n, and then some amplitudes an. So what it means is that if you go sufficiently far on the tail, the leading exponential will dominate, so the one with the smallest value of lambda. And the tail, therefore, the tail always has an exponential decay and not a Gaussian decay. In cosmological perturbation theory, the statistics is Gaussian or maybe almost Gaussian. You can have some small FNL corrections, but they never give rise to exponential tails. So this is the first very important difference. So just a small note on those values lambda. So mathematically, they correspond to the eigenvalues of the Fokker-Planck operator. And they can be computed analytically for a few models. For instance, if you have a flat potential with a width which is given by delta phi, and the height of the potential is given by v, this small v naught here, which is the potential height in Planck units, then you can construct this mu squared parameter, and lambda n is given by this combination. So you see that, for instance, if mu is very large, so if the width of your flat region is very large, well, then the values of lambda will be small, which means that the tail will be very heavy. So you will have a very slow decay on the tail. And typically in that case, you would produce way too many primordial black holes. While if mu is a small number, so if the width of your flat region is sufficiently narrow, then lambda is large, and therefore you have a strong exponential suppression and you produce much less primordial black holes. You can also look at what happens if you add a small constant slope in your potential. So instead of having a flat potential, you take a potential with a linear piece. And then you find that the eigenvalues that we had before are exactly the same, but they are shifted by a constant term, which is this alpha squared over v naught. Alpha can be small, but v naught is also typically very small. So depending on the ratio alpha squared over v naught, you might either give a small shift or a large shift. And if this term is large, it means it gives a large exponential suppression, and then it reduces by a lot the abundance of black holes. Now, the interesting model, I think, is this one. So you consider a cubic inflection point, so a potential which does like this. You have a cubic inflection point when phi equals 0 here, the derivative of the potential and the second derivative of the potential vanish. And then in that case, the eigenvalues lambda n, they take this form, where v naught is a small number because it's the energy density in Planck units. Alpha is a small number as well. So the lambdas, they are always small. And that means that the tails are always super heavy in those models, meaning that you produce way too many primordial black holes. Okay, so this is just a plot of a model where you have this cubic inflection point, which is the term controlled by beta here. We have also added a linear piece just to make generic potentials. It's not exactly a flat inflection point. It's like slightly broken to make it, not too specific to the flat inflection point condition. The solid lines correspond to the full distribution function in this model, and you can see that if you go far on the tail, it's a logarithmic scale on the vertical axis. So the fact is that it's a straight line shows that it's an exponential decay behavior. Close to the maximum, the Gaussian approximation gives a good fit to the full result. And this is, of course, something that you want, because you know that the most likely fluctuations, the one that you see on the CMB, they have Gaussian or quasi-Gaussian statistics. But if you move far on the tail, you can see that they have those exponential tails. Now, if you ask the question, what is the abundance of primordial black holes, which would correspond essentially to the integral of those curves above a certain threshold, the solid blue line here is the full result. The dotted line is what the Gaussian approximation would give you. So what you would obtain doing just standard cosmological perturbation theory. And you see that there are many, many orders of magnitude difference between the two results. So the Gaussian approximation vastly underestimates the number of black holes. I also would like to add that if you wanted to improve standard cosmological perturbation theory by including, say, FNL corrections or perturbative corrections to the Gaussian behavior, then that would not help. Okay, so that it will slightly increase, slightly shift this dotted line here, but still many, many orders of magnitude away from the true result. And the true result is essentially that in those models, you always overproduce primordial black holes, which is also quite a strong result. The only caveat is that this is obtained assuming Sorel. So of course, if you violate Sorel as you approach the inflection point, then you can evade this. But any inflationary model with a flat inflection point where you do not violate Sorel is immediately ruled out because it overproduces primordial black holes. Okay, so let me just keep an eye on the time. Yeah, I think I'm doing okay. So I also quickly mentioned that the examples that I've shown on this slide all correspond to single field Sorel models, but this can be extended to other types of models. For instance, if you have a model with a phase of so-called ultra Sorel. So ultra Sorel is a regime in the inflationary dynamics where the slope of the potential is so small that you can neglect it. And then the field is just moving because of its initial velocity and slowing down because of Hubble friction. So this is something which is very far away from the Sorel attractor. And in those cases, you can also reconstruct the distribution function of the first passage time. This is just a plot. In logarithmic scale, you see that it goes to a straight line. So the color bars are numerical. So numerical reconstruction. So we simulated a large number of long-term realizations, and then we constructed the PDF. The black line is some analytical estimate, which works well, and which shows that again on the tail you have this exponential behavior. Okay, so the main message here is that tails have exponential decays in cosmology always, and this means that if you want to study something which comes from the tails, like primordial black holes, you do need to go beyond standard perturbative techniques, which cannot account for those exponential tails. And when you do that, you typically find that you have way more extreme objects than what you would expect using a Gaussian assumption. And the reason is that an exponential decays much more slowly than a Gaussian function. Okay, this is essentially this. So before I stop, let me just mention quickly one other thing, maybe two things, depending on time. One is that even though those stochastic effects are mostly seen on the tail, and therefore they're relevant for extreme objects such as primordial black holes, they might also leave an imprint for more conventional cosmological observables, such as the power spectrum. Okay, so in the setup that I've explained, the stochastic delta rent formalism, one can also compute quantities like the power spectrum, which is a two-point function of my curvature perturbation. And in this paper, in this recent paper with Kenta Endo, we have shown that the power spectrum is given by this expression. So let me quickly explain what it means. So the delta N2 here is the standard deviation of the number of e-folds realized from a certain initial point phi naught to a final point phi star. Of course, it's expected because this is a two-point function, you expect somehow to have the two-point function of the duration of inflation somewhere. But this guy is convolved with this quantity, which is the backwards distribution associated to the field value at a certain number of e-folds before the end of inflation. So let me explain what it means. You take a certain scale k at which you want to measure the power spectrum. You know that that scale crosses out the Hubble radius, say, I don't know, 50 e-folds before the end of inflation. Then you ask the question, where is the field 50 e-folds before the end of inflation? The answer is stochastic. In the classical picture, there is a deterministic answer to that question. In the stochastic world, there is not. You just have a distribution function, which we call PBW for P backwards. And this can be computed also analytically. I mean, we have explained how to do it in this paper. And you convolve this standard deviation with that distribution. Okay, what it means, the main difference with the standard result, of course, if you do an expansion around in the limit where the noise has a small amplitude, you recover the standard result. But otherwise, the main difference with the standard result is that this comprises an integration over the full inflating domain. So if you look at a certain scale K, you don't probe the potential at a certain field value phi star, you probe the full inflationary potential because of this distribution function. So this is great because it tells you that in principle, you can also constrain the potential in regions that will be inaccessible in the classical theory. So let me just show, of course, a slightly extreme example, but just an example to make my point more clear. So here I consider a model where you have a phase of classical inflation. So here it's just a straight line, but it's a schematic plot. Okay, so I assume that this first classical region is just m squared phi squared for simplicity. But on top of my m squared phi squared potential, I add a last piece of the inflationary dynamics where the potential is exactly flat for, say, a couple of e-folds, and then inflation ends. So in this region, you have a lot, I mean, the dynamics of the field is mostly driven by the stochastic fluctuations, right, by quantum diffusion. And in this region here, it's driven mostly by the slope of my classical potential. And this is a plot of what I obtained for the power spectrum in this model. So this is power spectrum as a function of the wave number. The black dashed line is the classical result. So it's the result for m squared phi squared without this quantum well region. And the colored lines are the result in the full theory where mu, I mean, I have introduced mu before, but remember that mu is essentially a measure of the width of this region. So when mu equals 0, you get the black dashed line. This is mu squared equals 1, equals 3, 5, and 7. So as mu increases, you enlarge the quantum well, and so you have a larger and larger deviation from the classical result. Now, the point that I would like to make is the following. So let me consider, for instance, this case where mu squared equals 7. So if mu squared equals 7, the mean number, which is the red line here, the mean number of e-folds which is realized in the quantum well is of order 7, because mu squared also happens to be the mean number of e-folds. So it means that schematically, the scales which are impacted by quantum diffusion are the 7 last e-fold scales before the end of inflation. So that means you go from 0 here, which is the end of inflation, and until -7. And this is the range of scales which have a direct imprint from quantum fluctuation, from quantum diffusion. Now you can see from the plot, this is not what happens in the power spectrum. The power spectrum is affected all the way up to scales of which emerge 50 e-folds before the end of inflation, and those scales, they correspond to CMB scales. So you can, and I will explain in a second the reason why, but you can see that in a model where only the last 7 e-folds are impacted by quantum diffusion, this leaves an imprint in the cosmic microwave background, which in principle only probes what happens 50 e-folds before the end. And the reason for this large deviation is that 50 e-folds before the end of inflation, in some cases, you can be in the quantum well because this is a stochastic process, right? So it could happen that you go down the classical slope and then instead of spending 7 e-folds here, which is the mean value, you happen to bounce here back and forth and spend way more e-folds, and then you go out. So those cases are very rare, but because they give a large contribution to the power spectrum, they happen to give a significant deviation with a spectral index which become very, very blue here. And of course, this is ruled out because at CMB scales, we know that NS is is 0.96. But the conclusion of this discussion is that by properly accounting for stochastic effects, even by looking at the CMB, which in principle is something which in principle tells you something about the potential in the large field domain, you can put some indirect constraints on the full potential shape. Of course, you cannot see the details of what happens here, but you can say something like you can say that if there is a quantum well towards the end of inflation, it cannot be with a width which is larger than mu squared equals, say, 5 or 6. Okay, I think my time is almost over. I just very quickly advertise this recent paper with Yuichiro Tada, in which we did a careful analysis of abundance of remote black holes in the stochastic delta rand formalism. So starting from the statistics of the first passage time, we explain how we can extract the statistics of the density contrast. as well as of the compaction function. I just flash formulas that I don't explain, but essentially there are techniques that you can design to reconstruct objects which are relevant for primordial black holes, so the density contrast and the compaction function. And then we were able to derive mass distributions of primordial black holes. And of course, we find that the result is imprinted by quantum diffusion at many places, and doing a classical calculation, you would get something which is completely different from that, which again illustrates the need to take quantum diffusion into account. Okay, so let me just conclude and recall the main point that I've tried to make today. So what I've tried to explain is that the back reaction of vacuum quantum fluctuations on the dynamics of the background universe can be incorporated within the formalism of stochastic inflation, and that those back reacting effects are necessary if you want to describe routines which lead to large fluctuations, such as those yielding primordial black holes. The main message I want to convey today is that a generic and unavoidable conclusion of this analysis is that quantum diffusion leads to exponential tails, which is a non-perturbative breakdown of Gaussian statistics. So it's not something you can describe with FNL, GNL types of parameterization. So you do need to go beyond that. I've also tried to say that most, even if I was a bit quick on that, that most cosmological observables can be reconstructed from the first passage time analysis. So I've shown you the example of the power spectrum. I very quickly mentioned the example of the mass function, so the distribution, the one-point statistics of the density contrast and of the compaction function. And of course, in principle, so there is a lot of work which remains to be done, but one could expect to also be able to reconstruct endpoint functions like the bispectrum and so on. So this is not something that we yet know how to do, but it's something which I think should be studied. And finally, another point that I've made is that quantum diffusion makes the CMB probe the whole potential in principle, such that models leading to primordial black holes, which contain a phase dominated by quantum diffusion at the end of inflation, in fact, they are already constrained by the CMB, even if the two sets of scales are well separated. So you cannot just treat the CMB channel and the PBH channel as being separated and just tweaking your potential to match the CMB and tweaking your potential to match, say, desired distribution of primordial black holes. The reason is when you do that, you induce a phase dominated by quantum diffusion at late time, and this will have an effect on CMB observables. So you have to do those two things all together in a consistent way. Okay, so with this, I just stop and thank everyone for their attention.